Hi, y'all. It's Ms. Blasky. Today we're going to talk about topic 2.4, which is how we actually use these redox reactions to accomplish stuff. So we're going to talk about electrochemical cells. So this is pretty much what a battery is. So two different categories of electrochemical cells that we're going to talk about. There are galvanic cells, which you see here on the left. These are thermodynamically favored chemical reactions. It happens on its own as soon as you plug everything together. The other type of electrochemical cell, and we're not going to talk much about this one until a little bit later on in this unit, is called an electrolytic cell. So an electrolytic cell is a thermodynamically unfavorable reaction going on, which means that we need to provide an external source of the electrons, such as plugging it into the wall or some other sort of power source, to force those electrons to move and make that redox reaction happen. So the galvanic cell, this one on the left, is much more likely. This is what we see when we have batteries running. An electrolytic cell, this is very useful in industry. And this is how we plate metals on top of other metals. But it's not something that we see so much in everyday life. So let's talk about all the different parts of we're going to specifically talk about a galvanic cell first. So this is all vocab, all things that you need to be able to label and identify on a picture, and to talk about what's happening, use these vocab words. So the anode is the electrode or the metal chunk that is where oxidation occurs. As oxidation occurs, remember, oxidation is losing electrons, which means that those the metal atoms that make up that metal chunk are going to lose electrons, and they're going to go from being a metal to being a positive ion. Give me a minute and we'll show an animation of how all this works. So usually the anode tends to decrease in mass over time as this reaction occurs. On the other side of our cell, we have the cathode. This is where reduction occurs. So on this side, we are gaining electrons. The ions that exist in the solution will gain electrons and form on the surface of that metal electrode and start to increase the mass of that cathode electrode. You need to remember which one happens at which ion, sorry, my words are getting mixed up. What process happens at the anode and which process happens at the cathode. The silly saying is anox and red cat. So anox means at the anode you have oxidation. Red cat means you have reduction at the cathode. Sometimes one of these electrodes might be what we call an inert electrode. Maybe we're trying to oxidize or reduce a gas instead of a solid liquid combination. Or we're trying to do, maybe we're just trying to change ions from one ion to another ion. We can have a galvanic cell that changes Fe+2 to Fe+3. So in that case, we want an electrode that's not necessarily going to interact with what's going on. So in that case, our electrodes could be made out of platinum, or they could be made out of graphite, carbon. That happens a lot because those are not going to actually take place in the reaction, but they will still provide that location for the oxidation or the reduction to occur. Somewhere in that galvanic cell, there needs to be some sort of process to help maintain a charge neutrality. So we've got two different possibilities for this. So here's two different ways to be able to set up that galvanic cell. One system that we can use to maintain that charge balance is called a salt bridge. So in that salt bridge, we would place a neutral ionic solution. Sodium nitrate is really common, or potassium nitrate, because neither sodium nor nitrate or potassium will form precipitates with any other ionic substances. So we know that they're not going to influence what's going on. So in that salt bridge, the positive ion in the salt bridge will migrate towards the side of the galvanic cell that is losing positive charge. And then the nitrate will migrate to the side that is losing negative charge. So that helps maintain the charge balance in there. If we did not have a salt bridge in a galvanic cell, it wouldn't go. It would just stop. There'd be no transfer of electrons because we need sort of a way to keep that flow of electrons and that flow of charge constant. Another way to do this, instead of preloading a salt bridge with a different chemical, sometimes we can have something that's just called a porous disc. This is often made out of thin, unglazed ceramic. So it's got lots of holes inside of it. It allows those ions to migrate across the disk so that it might allow the negative ion from this side of the cell to migrate across here to bring some negative charge to the right. It might allow the positive charge from the right-hand side to migrate over and bring some positive charge to the left-hand side of the cell. But again, you have to have one of those two things in order to maintain your charge balance going on. In an electrolytic cell, that salt bridge or porous disc is unnecessary. So those only are going to happen in galvanic cells. All of these other pieces exist in both cells. We should always be able to identify which direction the electrons are flowing. The electrons always flow through the wire from the anode to the cathode. So in both galvanic and electrolytic cells, that electron flow can be labeled. So the electrons are traveling through this metal, through the wire, down into this other metal electrode. So we should be able to label that on any sort of drawing. Excuse me. The way that I always remember that is it goes alphabetical. From the anode to the cathode, it goes from A to C. That's alphabetical order. Oftentimes we will put something called a voltmeter or sometimes an ammeter onto this wire to measure the flow of electricity through that wire. So we could put a voltmeter here and it would tell us how many volts of electricity are flowing through the wire. We can put an ammeter here, which would tell us about the current, which tells us how fast those electrons are flowing. Or we could power something by placing it in this pathway of the wire. I could put a light bulb, I could put a fan, I could put whatever I need to power into that system there. For an electrolytic cell, the point of electrolytic cells is not to power them because they don't flow on their own. We have to provide our own power into that system. So we would put some sort of power source here. We could plug a battery into here, something else to force those electrons to start flowing. And then the important thing to know is that the solutions down in these containers are ionic solutions. They are electrolytes, which means they allow electricity to flow. If we had just pure water down here, this process would not happen because pure water does not transfer electricity. It cannot move those electrons around. We need those positive and negative charges in the solutions themselves to help that electricity flow. So that is all the parts of these cells. Now let's take a quick look at a close-up particle level video of how all of this works back and forth and see how things change. All right, this is a little old school, but I really like the way that they show the animations. So let's go back for just a quick second. So here we've got the setup for a galvanic cell. Here's my salt bridge. Here's one of my half cells. Here's the other. I've got two metal electrodes down here. One is the anode, one is the cathode, and those metal electrodes are connected by a wire. So now if we zoom in to the system, we can see what's happening. So here at the anode, we've got a zinc metal solution, a zinc metal electrode, and then a zinc +2 solution surrounding it. As those electrons lose, or those zinc atoms lose electrons, the atoms actually come off of the electrode, allowing the mass of that electrode to become smaller. Those electrons that were removed from the zinc ions now travel through the wire into the other compartment of our cell, into the cathode, where those electrons sort of coat the surface of the metal, and as the copper ions come into contact with that metal electrode, they form new copper metal atoms onto the surface. So that's our reduction in our cathode. Now in our salt bridge, our salt bridge is full of sodium nitrate. So some of the nitrate ions we can see coming out of that bridge into the anode compartment, because we're making more zinc ions, so we're making more positive charge, we need to add more negative charge to keep a charge balance. Some of those zinc ions also might actually go in to that salt bridge to help maintain that charge also. And then on the cathode side, some of the nitrate ions, some of the negative ions from the cathode compartment might be coming in, and some of the positive ions from the salt bridge are going to enter into the cathode compartment to help balance out that charge. Because remember, on this side, we had copper ions forming copper metal. And so this is losing some of its positive charge. We need to replace some of that positive charge. Sodium is the easiest way. The other thing that we can talk about with electrochemical cells is cell potential. So that is that actual amount of electricity flowing from one side of that cell to the other. So we measure this in volts. This is a voltage. In a galvanic cell, sometimes galvanic cells are also called voltaic cells. So just know that those two names mean the same thing. Galvanic and voltaic cells will end up with an overall positive cell potential, because that is our spontaneous or our thermodynamically favorable cells. Electrolytic cells are overall going to have a negative cell potential when we put all of those together. So the cell potentials for each individual half reaction is what I gave you on that extra blue sheet of paper. This is a listing of every possible cell potential you could ever need to know. So on the AP exam these days, they are giving you smaller versions of that chart with a fewer number of half reactions that you might need for solving that particular problem. Back in the olden days, they just gave you the sheet on the back of your periodic table and you had to look them all up. So not all of the problems we're going to practice have the cell potentials that you particularly need in the problem. So I gave you that extra blue sheet just as sort of a backup in case there's a cell potential that you need that isn't given to you in a problem. So if you look at that blue sheet of paper, you can see that every single one of these reactions is written as a reduction. And often this is actually called the standard reduction potential chart. So these reactions up at the top have the largest reduction cell potential. Down as we get towards the bottom, these ones have a very negative reduction cell potential. So the reactions that are closer to the top of the chart are more likely to be reduced. The reactions down at the bottom part of this chart are much more likely to be oxidized. Remember that we can, oxidation is losing electrons, so we can actually take these reduction potentials the way they are written and flip them backwards, just like we flip things when we talked about delta H. So if I take one of these reactions and I switch the reactants and the products, then I also am going to switch the sign of the cell potential. So if I take this lithium reduction that has a cell potential of negative 3.05, I could flip this around to be oxidation. And as an oxidation reaction, it would have a cell potential of positive 3.05, showing that it is much more thermodynamically favorable. when we have two half reactions, we can look up those two half reactions on our chart and identify what's going on. So here for number 7, I've got the balanced equation, actually it's not balanced, of aluminum +3 plus magnesium going to aluminum and magnesium +2. So I can write this out as our two half reactions, just as we were doing before. I've got aluminum +3 going to aluminum. And then I've got magnesium forming magnesium +2. No extraneous balancing on these because there's no hydrogens and no oxygens. So I just need to balance my electrons. So if I've got 3 electrons on here to make that charge balanced, I've got 2 electrons over here to make that charge balanced. So now I can go and I can find these reactions on my reduction potential chart. So I go back to that chart. I've got aluminum. Hey, look, I'm already sort of zoomed in on it. Aluminum +3 electrons makes aluminum solid. As a reduction, that is -1.66. And then I've got magnesium. Where's my magnesium? Oh, right under it. Magnesium here as a reduction is -2.37. So 1.66 and 2.37. So -1.66 the way it was written. And then magnesium, this is written as an oxidation. So I need to flip that around. So that's going to be +2.37. So there's my cell potentials for those two half reactions. Now I can get my balanced equation overall. I've got 3 electrons going in, 2 electrons going out. That's not balanced. I'm going to multiply this guy by 2. I'm going to multiply this guy by 3. So overall, 6 electrons plus 2 aluminums plus 3 magnesiums makes 2 aluminum metals plus 3 magnesium ions plus 6 electrons. Those 6 electrons are going to cancel each other out. So my overall balanced equation is 2 aluminum plus 3 ions plus 3 magnesium make 2 aluminums and 3 magnesium ions. So now to find the cell potential for this, so we write this out as E0 cell. That 0 means we are at standard conditions. We'll talk about that a little bit more later. All I have to do is I have to add these together the way they're written. So 2.37 minus 1.66 gives me, let's see, what would that be? I don't have my calculator on me. So this gives me a result of 0.71 volts. So my cell potential is positive. I know that this is a possibility for a galvanic cell. They told me it was already, but I know that it can be true for a galvanic cell because that is an overall positive cell potential. So we will keep talking about these in class. A lot of it is just looking up things and sort of relying on some of those rules that we learned about balancing chemical equations. All right. I will talk to you all in class. See you later.